Hello everyone. In today's video, we are going to be starting with a new chapter, which is chapter 5. And in this chapter, we are going to be dealing with complex numbers. So this is an entirely new set of numbers which you have never learned before. Earlier, you had studied about natural numbers, you studied about integers. Then when you go to higher classes, you learned about rational numbers and then irrational numbers. And then when you move on to class 10, you learned about real numbers. And then now that you're in class 11, you are going to study about complex numbers. Now, why do we need complex numbers? Let me write that down properly. So why do we need complex numbers? Let's just look into the history of why there was a need to bring about a new set of numbers. So mathematicians were trying to solve this equation, x squared plus 1 equal 0. So if I ask you to solve this, you would solve and tell me that the value is root over minus 1. But the problem is, what is root over minus 1? It's not a natural number, it's not an integer, nor is it a rational number, an irrational, or a real number. So what is this number? They could not figure out, and that's when they introduced a new set of numbers, which we now call them the set of complex numbers. So that's the history about how complex numbers came into existence. Okay, so let's see, how do we denote complex numbers? So our heading will be complex numbers. Usually, complex numbers are denoted by the small letter z, and a complex number is always made up of two parts, a, and the second part is I times b. A and b, they are real numbers. Remember that. They are real numbers. But what is I? The value of I is equal to that root over minus 1 that we could not solve. So this is the value of I. I has a special name. It is called iota. All right? So this is how we denote complex numbers. Complex numbers are always written in the form a plus I times b. A and b are always going to be real numbers, and the value of I is root over minus 1. So this is important. You need to write this down. What is a? A also has another special name. Of course, it's a real number, but it's also called the real part of z. The real part. And b is called the imaginary part of z. Okay? These are the special names that are given to these two real numbers that combine to form a complex number. Now let's move on to another topic, which is equality of complex numbers. So when do we say two complex numbers are equal? Let's say we have our first complex number, z1, which is written as a1 plus I times b1, and we have another complex number, z2, which is written as a2 plus I times b2. So what does it mean if I say z1 is equal to z2? This will mean that a1 is equal to a2 and that b1 is equal to b2. That's the only way we can say that two complex numbers are equal. It's a simple topic. I'm sure you understand. Let's move on to another topic, which is the algebra of complex numbers. So when I say that I want to study algebra of complex numbers, it means I want to know how complex numbers are added, subtracted, multiplied, etc. So first thing first, we are going to learn about the addition of complex numbers. So let's consider two complex numbers, z1 and z2. So if I am supposed to add these two complex numbers, it would mean that I need to add their real parts and their imaginary parts. That's how I add two complex numbers. Subtraction also follows in a similar manner. If instead of addition we put the subtraction symbol, we will have minus over here, here, and here. Fine? Now let's study more about addition of complex numbers. Let's look into the properties of addition. The first property that we are going to study is known as the closure property. What this property says is that if I have z1 and z2 as real numbers, and if I add z1 and z2, I will get an answer, let's say z3. Now this property says that z3 must also be a complex number. So if you want to understand this better, let me just give you an example in terms of real number. If I take 2, it's a real number, and I take 3, that is also a real number, and if I add them, my answer is 5, which is again a real number. So I took two real numbers and I got an answer which is also a real number. So that is called closure property. In a similar way, that's what I want to explain about complex numbers. You take two numbers, add them up, and whatever answer you get, it is always going to be a complex number. This is known as the closure property. The next property that we're going to learn about addition is known as commutative property. Okay, so let's study this property. If I take two complex numbers, z1 and z2, and I add them in this order, and then I also add them in a different order, where I put z1 first, I will find that both the answers will be the same. This is known as commutative property. Even in real numbers, this property exists. If I take 2 plus 3, I get 5. If I calculate 3 plus 2 as well, I get 5. In both cases, the answer is the same. So this is known as the commutative property. The next property we are going to discuss is known as the associative property. Now this property says that I will add z1 and z2 first, and whatever answer I get from there, I will add with z3. This will be the same as me adding z1 with whatever I'm going to get if I add z2 plus z3. So it does not matter how I group my three numbers, okay? The answer will still be the same. So let's take a look at what this associative property would look like in real numbers so that you'll get an idea. Let's say I do 2 plus 3 plus 4. I know this is 5 plus 4, which is 9. Now let's switch up the brackets. Let's say I do 2 plus 3 plus 4. Using BODMAS rule, I will always solve inside the bracket first. So I'll get 2 plus 7 and the answer is 9. So it does not matter how I group my numbers, the answer is still the same. This property is known as associative property. The next property we're going to discuss is about the existence of the additive identity. And that means if I take a complex number z I will add it with what so that I will get my answer to be z again. Obviously, we know that it's only possible if we add z with 0. This 0 is also a complex number because it can be written as 0 plus I times 0. So it is a complex number. So if there exists such a number, which when I add with a complex number, I will get back the same complex number, then this particular number will be known as the additive identity. Alright? So please remember, an additive identity is a number which when added to my complex number, I should get back the same complex number. The next topic is existence of additive inverse. So that means if I take z, I need to think of another complex number which when I add to z, I will get the additive identity. This would be possible only if we consider minus z. So if we have z with minus z, let me write that one properly, it doesn't look good. So if we have z and minus z, okay, and we add them together, we will get 0. So we say that the additive inverse of z is minus z. Alright? So those are the 5 properties. We have closure property, which we had studied, commutative, associative, existence of additive identity, and existence of additive inverse. Next, we're going to discuss about multiplication of complex numbers. That means z1 multiplied with z2. That means a1 plus I times b1 multiplied with a2 plus I times b2. So let's solve this. a1 multiplied with this, we will get a1, a2. Then we will have a1 multiplied with I times b2. Then next is going to be I times b1 multiplied with a2. And then finally we'll have I square b1, b2. Let's simplify this. This is going to be a1, a2. And from these two middle terms, I can take common I. So I'll get a1, b2 plus b1, a2. And I know that the value of I is equal to root over minus 1, right? And I had shown you earlier that if I square I will get minus 1. So this value I square is minus 1. So that means I'll not put a plus there. I will put minus b1, b2. So I'm going to group the parts that do not contain I together and those containing I together. So we will get this part is the real part of the product z1, z2. And this part over here is going to be the imaginary part of z1, z2. So it's better if you learn by heart this part, that the multiplication of z1, z2 is equal to a1, a2 minus b1, b2 plus I times a1, b2 plus b1, a2. So that you will, you don't have to do these 3 steps. It'll make your calculation much easier and faster. So I would recommend that you learn it by heart. But in case you forget, you can always deduce it doing these 3 steps. All right? So I hope you understand how we multiply complex numbers. Now let's look at properties of complex numbers. Properties of multiplication of complex numbers, I mean. So the first property is the closure property. If I take z1 and z2, and they're both complex numbers, and if I calculate this product, it should also be a complex number. I hope it makes sense because I've given a detailed explanation of closure property when we did addition. So the concept is the same, but it's just that instead of the operation plus, we have into. Then we have commutative property. That means if I multiply z1, z2, it's the same if I multiply z2, z1. The answer will be still the same. That's the meaning of commutative property of multiplication. And associative property means, let's say I multiply z1 and z2 first, and whatever I get from there, I multiply with z3. Or what I do is I first multiply z2 with z3, and whatever I get from there, I multiply with z1. Whichever way I group the numbers, the answer is still the same. So that's the associative property. The next topic is the existence of multiplicative identity. So let's say I take a complex number z. What should I multiply it with in order to get back z? If it were addition, I will add 0. But here I cannot multiply with 0, because if I multiply with 0, my answer will be 0. So which complex number, which when I multiply with z, I'll get back z? Obviously, it is 1. 1 is also a complex number because it can be written as 1 plus I times into 0. And if I solve this, I'll get 1. So you see, any real number is also a complex number. It's just that a real number has the imaginary part to be 0. So here 1 is called the multiplicative identity. Let's talk about the multiplicative inverse. We denote it as z to the power minus 1. So this multiplicative inverse is 1 by z. And that means 1 divided by a plus I times b. Suppose I want to, you know that method of rationalization? Okay, I'm going to follow that method, similar to that. What I'm going to do is, I'm going to do this. I think you've seen this somewhere. Anyway, so what you're going to do is multiply both numerator and denominator by a minus ib, okay, by the conjugate. We'll discuss about the conjugate after some time. So you'll get the numerator to be a minus ib, and if you look at the denominator, it follows that formula a square minus b square. So a square minus, here it's not b square, it's going to be ib whole thing square. So if you solve this, you'll get a minus I times b divided by a square. You'll get I square, right? And we know that I square is minus 1. So minus 1 and this minus will become plus b square. So you can skip all this part and simply write down the value of multiplicative inverse of a complex number is a minus I times b divided by a square plus b square. There's a geometric meaning for this, and we will discuss it later. Okay? So those are the properties of multiplication. Then there's another property known as the distributive property. Now this property is a combination of multiplication and addition. Say you have z2 and z2 and z3 that are added together, and whatever you get from there you multiply with z1. And the answer will be z1, z2 plus z1, z3. That means you're distributing z1 with z2 and also with z3. That's why it is called the distributive property. You could have it the other way around as well. Suppose you have the addition of z1 and z2 multiplied with z3. So it will follow the same logic. You'll get z1 multiplied with z3 plus z2 multiplied with z3. This is known as the distributive property. Why? Because we're distributing z3 with z1 and also with z2. Okay, let's move on to another topic, powers of I. So we know that I is equal to root over minus 1, and that when we square it, we will get minus 1. How about when we take the cube of it? The cube is equal to I times I square, isn't it? Or in other words, I square times I, which means minus 1 into root over minus 1, and this means minus I. Okay, let's see. I to the power 4. This means I square into I square. And that means minus 1 into minus 1, and that means 1. Let's look at I to the power 5. You will get here I square into I cube. I know that I square is minus 1 and that I cube from here is minus I. So minus to minus is plus, so this will give me I. Then I want you to continue on your own and calculate I to the power 6, I to the power 7, I to the power 8, 9, 10, etc. Do this and you will notice a certain pattern. You will notice that the value minus 1 gets repeated after some time. Then minus I also gets repeated, I, 1 and I. Just give this a try, alright? So give this a try, calculate all these values and you will see that these numbers, minus 1, minus I, 1 and I, they will keep repeating. And then what I want you to do is, I want you to check for which value of I mean for which power of I. When I is raised to what power, you will get minus 1. And then I want you to check when I is raised to what power, your answer will be minus I, etc., etc. Okay? So that will be your assignment. You please try that. You will see that there is a pattern. Okay, now let's discuss about something important. So like when we talk about real numbers, and if I multiply root A with root B, my answer is root over AB. This is true for real numbers, but this is not true for complex numbers. This is very important for you to understand. This is not true for complex numbers, although it is true for real numbers. For real numbers, if I calculate root over 2 with root over 3, this means root over 6. But for complex number, let's say I do root over minus 2 into root over minus 3. Let's calculate how much this is. This is root 2 into minus 1. No. Let me take a better example, not this one. Let's consider I square. We know that this value is equal to minus 1. But if we follow this pattern, okay, this one here, let's see what we get. We know this is root over minus 1 multiplied with root over minus 1. And if we are to follow this pattern, which says that root 2 into root 3 is equal to 2 into 3, right? That's what this pattern says. If it were real numbers, this is going to be true, okay? Like over here. So let's see, we will be getting minus 1 multiplied with minus 1. And this will give us root over 1, which is equal to 1. And that's not true because we know that the value of I square is minus 1. So what I'm trying to say is that this is not true. I mean, the fact that root over A into root over B equal to root over AB is not true when we talk about real numbers. So the point to remember, I scribbled so much in the other page, so let's look over here. The point is, when you multiply two real numbers, you cannot take those, not real numbers, sorry, complex numbers, you cannot ever write them in this manner. Okay, let's talk about identities. You know, z1 plus z2 whole thing square. It will follow the same, the same one that you'd learned in your lower classes. It will be z1 square plus twice z1 z2 plus z2 square. The same goes for z1 minus z2 whole thing square, and also for z1 square minus z2 square. So I'm sure you know these, so you can fill in the blanks by yourself. So the last part of the theory that I'm going to be discussing with you is the conjugate and the modulus. So conjugate of a complex number z is denoted by z with a bar. And if suppose, hold on a second. If suppose you have z and it is equal to a plus ib, then its conjugate, which is denoted by z bar, is always going to be a minus ib. We only change the sign of the imaginary part. So for conjugate, we only need to change the sign of the imaginary part of z. All right, so that's the conjugate. Now the geometrical meaning is this. We'll discuss about geometrical meaning later on in another video. So for now, just know that. Anyway, then we have the modulus. The modulus is denoted by z with these two parallel lines, and it is equal to root over a square plus b square. So this is the modulus, this one is the conjugate. Now, if you have a look at your multiplicative inverse, you will notice that the inverse is actually equal to the conjugate on the numerator, and it is equal to the modulus square in the denominator. You see this? Okay, so that means the inverse can be written as conjugate divided by modulus square. So that concludes our theory part of this chapter, and we will begin with problems in the next video. Okay, so that's all for today. Thank you very much.